Okay, let's get going. Hello, everybody, and welcome to LondonR on a very windy evening. I don't know what it's like for everyone else, but I think my fence is about to blow over. So we have three presentations tonight. Hopefully everyone can hear and see me okay. This is hosted by Mango Solutions. We were formed in 2002. We're based in Chippenham, Bristol, and London, and we empower organizations to make informed decisions using data science and advanced analytics. And we arrange and organize a whole host of data science events such as LondonR, Bristol Data Scientists. We have a data engineering meetup in London, and also the Earl conference, which I will touch on in a minute. Kind of what we've been getting up to while a lot of us are based from home. As far as we're concerned, we're delivering business as usual. We've been able to offer our training online and all of our consulting online as well. If you would like to present or speak at a future LondonR, please drop us an email. We'd love to hear from you. And then our big announcement, many of you might already know that we host the Earl conference every year. It's the Enterprise Applications of the R Language conference. And we usually host this second week of September in the Tower Hotel. Obviously this year we can't go ahead as planned. So we have decided to do Earl virtually instead. So from the 12th to the 16th of October, we'll be hosting a few different events via Zoom. So we'll be doing 4 workshops. We've announced 3 of these. We've got one on Golem, one on ggplot2, and one on text analysis. And then this is all kind of wrapping up on Friday the 16th of October with a day of presentations. So we've got 2 keynote speakers, and then the rest of the day is a single track of half-an-hour presentations on how people use R in enterprise. There's a small price for the presentation day, that's £9.99. The half-day workshops are £90. This is a huge reduction on what we normally charge for Earl in person. Obviously, we recognise we have less costs in terms of venue and food and all that kind of stuff. But by charging that, we guarantee that people show up. At free events, we often get 50% turnout, but because we're limited by the capacity on Zoom, we want to make sure as many people that want to come can come. So that's why we're charging. And any profits we're making, we will be donating to Data for Black Lives, which we're really excited about. So take a look at earlconf.com. We've got more details on the workshops and the full agenda as well for Friday. And then tonight, first up, we have Tim Johnson, who is presenting on, Tim, you've given me, this is a difficult topic, like title for me to read, so read that for yourselves. And then we've got Emma, and then finally Mark. So we've got a really great evening of presentations. Just a couple of housekeeping notices. If you could keep yourself on mute, that would be great while everyone's presenting. Also, just to be aware that this is being recorded, so if you don't want your camera on, if you don't want to be seen, just keep that off. If you'd like to ask any questions, please use the chat feature on Zoom. So just as and when you have a question, just type that. And at the end of each presentation, the speakers will answer your questions, just rather than everyone coming off mute and talking at the same time. So I think that's everything I wanted to say. So first up, we have Tim. So I'm going to stop sharing my screen and then hand over to Tim. So Tim, if you'd like to unmute yourself and share your screen, we'll get going.
Excellent. Let me know if you can see that.
Yep, that's all good.
Great. Okay, let me just see if I can minimize the video. Okay, perfect. Great. So today, like as Laura said, I'm talking about what can be quite a difficult topic. Now, I spent a lot of time during lockdown getting my head around some of this stuff. I'm Tim. I work for my own company, Psychonomic Consulting, and my background is marketing analytics. So yes, machine learning, but actually in practice, complicated regression models. And one of the things we have to do through the sort of time series, measuring the impact of promotions, price, distribution, seasonality on sales or other KPIs is actually, it turns out, some of this stuff here. And so I'm talking about hyperparameter tuning and pipeline optimization. And I'm going to talk in the context of if someone knows nothing about this stuff, hopefully in 20 minutes time, they'll know a heck of a lot more. and actually be able to think about how they could use some of this stuff and apply it to data science and machine learning models that you might be building at work. So I'd be quite keen to know how many people know what a hyperparameter is. I don't know, Laura, if you can set up a quick poll to ask that. If you don't know answer, that's absolutely fine. But if you do know what a hyperparameter is, I'd quite welcome just knowing that. And I'm going to get started. Okay. So I've got 5 recommendations. Firstly is measure your decisions. Now, in the context of modeling, one can spend a lot of time talking and actually a surprising little time actually quantifying the impact of the difference that a decision can make. So my first recommendation really is, if you're building a model and you're making decisions about your model, then find a way to actually measure the impact of those decisions. And that'll help you understand, well, how important was it? We spent a lot of time talking about it. And yes, indeed, it did make a difference. It's worth thinking about next time, but also help you choose best approaches and help you make some of those decisions. Now, machine learning can be a difficult topic. I've got an analogy that I'd like to use, which is taking photos with a camera. So I'm not a photographer, so if I get some of this stuff wrong, please forgive me. But I've seen my wife take photos, and she's had this dial on the left. It doesn't mean anything to me. But depending what she's taking a photo of, you can see here 2 images. One's quite far away, a lot of light. One's quite close up without. I think that the sun is from a different angle here, potentially behind. And you're going to need a different dial if you're taking a photo to get that quality image. And it turns out that these settings on a camera are actually reasonable analogy for what a hyperparameter is. So quite a complicated slide, my apologies, but what do cameras do? They ultimately, in my view, they capture light. And as a result, we get an image. So the camera's in the middle of this slide. What does that do? It turns light into images, as I've just said. On the left, we've got inputs. So what we're looking at, the landscape, but also the light, clearly, that's coming in. And they get turned into outputs. So pixels, images. But then what affects that, as I've just said, is the camera settings. And it turns out that these 3 things, the aperture, the shutter speed, the ISO speed, they actually control how the camera works and how the inputs get turned into outputs. And different combinations of these can actually give similar results. And there can be quite a lot of expert knowledge that's needed to actually work out, well, what combination of these for this data is going to work best to capture our image. So that really is one part of the puzzle. But it turns out that when you're looking at this stuff, well, actually, the data that you're collecting, it's not just what you're looking at, but there are other things as well. What time of day? Are you there in the evening? Is it the morning? Where are you stood in relation to what you're taking a photo of? And actually, as I said, where's the sun in relation to you? These things matters as well. So the data that you're collecting, what you're choosing to take a photo of, you're actually going to need different camera settings to get that quality image as a result. So what does this mean for machine learning? Well, what do machine learning models do? Ultimately, in my view, they capture data in order to create a prediction. And so we've got a model in the middle that turns data into predictions. That's ultimately what I believe we're wanting to do here with this aspect. So we've got inputs, we've got features, we've got outcomes. So we can describe the data, and there's something that we're wanting to predict. And then as a result, we get outputs. We get these things called parameters that are numbers that allow us to make predictions. And then in terms of the model, for a given algorithm, so if one's doing regression, one's doing decision trees, one's doing more complicated stuff on top. So if one is doing something like random forests, something like XGBoost, these ensemble models of decision trees, or if one's doing neural networks and actually complex deep learning, then this stuff becomes really important. And so I've got epochs there, fancy word. That's really how many times you might put your data through. So we can kind of think, okay, how many times are we going to look at the observations? We've got the features, and then we've got a fancy word, regularization. Another key setting, which is for our parameters, when we're making predictions, how much we might squish them to make sure we're not overfitting and learning noise in the data. So that's really our model. It's taking the inputs, creating outputs, and these hyperparameters, they're going to control how your model works. And so thinking about them, understanding them, really helpful. In addition to that, though, where's the data coming from? You know, I said time of day earlier. Have we got data that is going to represent data we're going to get in the future? That's really important to think about, because actually you might find that when you come to production that you actually don't. And really, what transformations are we going to make? So I started with features as the inputs, but as everyone who does this stuff knows, 80% of the time is really, okay, getting the data in shape, and feature engineering, which is creating variables that we can put into the model. Now, as I've said, more complex algorithms, they have these hyperparameters. So I've got here some simple code for doing random forests using the ranger package. Really, the point from this slide is we've got x equals features, so we're going to put in our features, we're going to predict the outcome, we're doing classification, but then there's all this other stuff. How many trees are we going to build? How many variables are we going to actually include in each tree? How deep are we going to include, allow a tree to build? How many observations are we going to allow in an end node in that each decision tree? How are we going to split? And the list really can go on. So these decisions need to be made, and really what I'm talking about is, well, how do we make them? So, as I've said already, recommendation 1, measure the impact. So do this stuff. And recommendation 2 is predict on new data. So for those who do this stuff, this is going to be old hat. But for those who don't know, this can be actually a really hard thing to absorb. So typically, we want to split our data into 3, and it can get a lot more complicated than that. But there's a key principle, which is if we've got what I've called train here, if you imagine that as a data set, so in simple terms, you know, a table in Excel or a database that contains our features, contains our outcome, has a certain number of rows for each observation. And we run that through a model. We get some numbers out that are the parameters of that model, so allow us to make predictions. And that's great. But if we're making decisions about how well different settings work for making those predictions, so if you go back to our camera analogy, if we're just working out the best settings for a certain mountain at a certain time of day, or even indeed, you know, a collection of photos, we're saying, okay, that's a good setting. We might well find that when we go somewhere else, we go skiing, well, actually, it doesn't work well. And so there's a really important thing of choosing some data to train a model, but then using a second data set to make decisions about that model. So one might make decisions about the hyperparameters, but would also might make decisions about, well, what variables are we going to put into the model? Are we going to do some simple sort of correlations between each feature and the outcome, and choose a cutoff, maybe 0.3, maybe 0.5 for the output of that? Those decisions really should be made on a separate data set to allow us to predict new data. And then thirdly, if we're doing that, ideally, we absolutely want to have some final data that says, okay, we've got the model, we've learned the parameters, we use some separate data to learn the settings, the hyperparameters, and then we've got some third data that says, okay, given all of that, how good are our predictions? Looking at the first two, there's a process of cross-validation I'm not going to go into now, but broadly that says, okay, instead of creating one split, let's do it several times. And that'll give us more confidence that when we're making predictions, we're not overfitting, and we're actually able to represent the quality of prediction that we'll get when we're in deployment and into a production environment. Quite a lot. So if you've not, if I've not explained that very well, it's absolutely something to think about in Google. Now, if we're doing cross-validation, here's a simple thing just to look at what we would do that. I'm going to move on. As I've said, choosing the settings that best predict new data is really important. You don't just want to focus on a single data set and use that to decide everything. You really want to be able to simulate what quality of predictions will we get for the new data that we're going to get in production. So thirdly, use the right approach. And this is really the sort of core, if you like, of what I was looking at. So in my view, there's 6 broad approaches to how we can tune and optimize hyperparameters and entire pipelines. So they're kind of into 3 buckets, 2 approaches each. Firstly, we've got tweak, and this includes, look, yeah, there's stuff I can change, but actually it comes with a default, or this is what I've used before, or this is what a colleague or Stack Overflow has recommended. Really something that is felt to work well in a number of situations. Equally, one might just tweak and actually say, okay, well, I've read about a certain, I've read the manual, there's this key thing that I can change. So on the camera analogy, let me just try different settings, take a photo, and see how the image compares. Do I get a better quality image, or in the model's context, a better prediction through different combinations of settings? And really what we're doing here is we're trying different stuff and actually then deciding, is that good enough? But it's arbitrary, it's manual, it's ad hoc. So then we've got the more structured approaches, testing. So this is thinking like an A/B test. There's something called grid search, where you literally are just testing all possible combinations. There's something called random search, which is where we say, well, there's too many possible combinations. In the field that I work, one could literally have certainly 100,000 combinations, but it actually can get into the tens of millions. And so then one can't try everything, because what we're doing here is we're building a separate model for each of them. But one can sample from the settings, so a Monte Carlo approach, if you like. But either way, what we're doing here is we're choosing the best predictions for many models, but we're doing so after the fact. We're taking a load of photos, and then we're working out, okay, they're all under different combinations of settings. Which one is giving us the best model or image as a result? Then you've got the next 2, which are optimize, and we've got this fancy word, stochastic optimization. This includes things like genetic algorithms. There were other approaches as well. There's quite a lot of approaches for optimization. Can fit within Markov chain Monte Carlo from a sampling perspective. And the difference here is, whereas with grid and random search, we're taking a load of photos and then we're just saying, what's a good one at the end. With stochastic optimization, we're taking some photos and then actually we're identifying which settings seem to be working well. And then we're keeping those settings and we're taking more photos. We're having a sort of combination of exploring new stuff, but then exploiting what is seen to be working well. So try lots of stuff, but then test more, and really an informed approach. And then finally, there's Bayesian optimization, which is far more complicated. People who are doing neural networks, deep learning, got very excited about this in the last 5 years. And this really is building a model of the impact that those camera settings are having on that image quality. So the impact that a deep learning structure, if you like, architecture is having on final prediction quality. A lot more complicated, but really testing models as one goes to reinforce best predictions. Now, they've each got pros and cons. The default's great for a classic algorithm. Something like regression actually there really isn't anything to choose, unless you're thinking about the pipeline, when you might well be filtering your variables and actually you are making a decision. It's in the context of a pipeline rather than the algorithm. But you might get a poor prediction quality as a result, but does work well for known results. The manual search, really good for a simple pipeline, but it is going to take some time. And so whilst it works well for a new approach, if you're learning decision trees, well, let's try stuff, okay, fine, I get some intuition here. It's not thorough, it's not rigorous. So the grid search is probably most common for people who are doing this stuff. Great for a complex algorithm where actually you want to make sure that you're getting the most out of it. But if you've got too many options, it's not going to work that well. So for a few key settings is going to be really good. Random search, if you've got a lot of options, as I said, this is going to work well, but actually it might be slow and it might not get you the best results. So if you've got too many settings for grid search, then absolutely this is something to consider. But ultimately, something like stochastic optimization is going to be faster. It may well get you a better set of hyperparameters, but you may well get a lot of models. So again, it might waste time. It's going to take time to program. And then Bayesian optimization, what's good here is it actually gives you fewer iterations. So whereas something like stochastic optimization, you may well run a couple of 100,000 models or more. Bayesian optimization literally could be tens of models. But for each one, it's building another model, a kind of pseudo model, and therefore it adds time. So it works well when your actual model itself, like a deep learning model, is expensive. So if you're running your model and it's taking time or is expensive to compute, then the Bayesian optimization is a good one. So I've got a kind of decision tree here to help you choose your approach. I'm not going to go through it in detail, but broadly, if you're confident to do stuff and you've got a complex algorithm, then you're in the middle here. If you've got complex algorithm and you're able to do more computation, both programming it yourself and actually having that running, then absolutely move on to the third approaches. So this, I think, hopefully is helpful for some of you to make decisions because ultimately, just got some more code here. If you've got a few key settings, then actually grid search is great. You don't have to use the most complicated approach, which turns me to my next recommendation, which is do not over-optimize. Because I see a lot of people spending hours actually just tweaking stuff or rerunning a grid search. Your time clearly is valuable, and you need to focus on, well, where's going to give me the most value in terms of prediction quality for that element of your work. So you can test everything, but you might well just say, okay, well, we're happy with the feature engineering. So yes, we could test that bit, but we've made those decisions. We're building a model that's similar to what we've done before. We're going to run a grid search on the hyperparameters. We're happy with the activation functions, how we're getting predictions from parameters. So don't over-optimize. Your time absolutely is well spent on other things. A single grid search may well get you good settings. You don't necessarily need to be rerunning this each time. But equally, using a structured approach and using the approach that fits well for the data that you've got, how confident you are with doing this stuff, and how much you're able to program, and what algorithm you're using or choosing from, it's going to dictate how much time you should spend on this stuff. So last recommendation, measure your impact. So what are we talking about here? We're talking about building models that make predictions, but ultimately, what do those models make predictions for is to add value. In my context for marketing, it's increasing revenue. It's reducing churn. So, stopping customers leaving us, being able to work out who's likely to leave and targeting them to encourage them to stay, or contacting them and talking to them in a different way. If you call Sky, you say you want to leave, they may well have a model that is predicting how likely you are to leave, and that'll influence the person you talk to as to what kind of offers they might give you. So whilst you will absolutely care about your model and absolutely should care about the quality of the predictions that you're making, all this stuff in the sort of green color there, there's all this stuff around that your department head and your stakeholders, boss and department head, are going to be thinking about, which is really, what's this doing for me? Is this giving me an output that is helping? Are we up year on year, and do we feel that is because of the complex stuff that the data scientists are doing for us? So models exist to add value, and so really thinking about how your model impacts KPIs and the other stuff that affects that as well is really important. So quantifying the impact of better predictions, whether to make a business case for more investment or just so you know how long you should be spending on this stuff, is really important as well. So I'd encourage all of you, if you actually have something in deployment, say you're building a model to work out what emails to send people, do an A/B test on your own model. Have some people who get something that would have been what happened before you guys got involved and changed the process. And then have other people who, of course, are affected by your model and respond in a better way. That'll allow you to see, okay, here's the impact that all our work has had. But then equally, if you're doing this stuff, you're spending time tuning, or you want to make a business case for being able to use a better algorithm or move to a deep learning approach, being able to talk in the executive KPIs and have at least a view. It's going to be rough and ready. It's not going to be precise, but having a view on, we think that it's in the region of this additional impact. We're going to, here's what we're doing already. If we move to this new approach, here's the additional gain we're going to be able to get. That is going to help make that business case for you. So measuring the impact of what you're doing, if you can, is really worth doing. So what have I said? Right, hyperparameters is like taking photos on a camera. You're changing the settings on your algorithm, but you've got your pipeline as well. You've got all the other decisions that you're making about the data that you're using, and that's going to affect the predictions that you're making. So measure those decisions where you can. Predict on new data so that you're confident that you're not going to get a disappointment in deployment. You don't want to be moving to a production environment and actually find that your model is far less effective than you expected. That absolutely can happen a lot. You want to use the right approach, so hopefully that decision tree is helpful for some of you. You don't want to over-optimize. You want to make sure your time is being spent effectively. There's lots of other stuff you could be doing with your time. And ultimately, measure your impact. Make sure that you're not just really clever and really whizzy with data, but that you're able to talk to the financial impact or executive KPI impact that your work is having. That will help tremendously if you're having to make asks in terms of more resource, more time, capability, etc. Hope that's been helpful. I'm happy to answer any questions. Thank you.
Thanks a lot, Tim. That was great. Yeah, if anyone has any questions, feel free to type them into the chat or feel free to unmute yourself and ask away. If not, feel free to connect with Tim on LinkedIn. We can, if you have LinkedIn, Tim, I can share that with people and people can come to you with any questions. Okay, great. Thank you so much, Tim.
Thank you, everyone. Have a good evening. Cheers.
Cool. So if you'd like to stop sharing your screen. And then next up, we have Emma. Great. Thank you very much, Tim. Cool. Emma, whenever you're ready, if you'd like to share your screen and take it away.
Perfect. I'll even start my video and hopefully you can see my...
Oh, we've just had some questions come through, actually.
Okay.
Tim, can you see the questions or would you like me to read them to you?
Let me have a look. Okay, sorry, polls aren't loading, no problem. In the slides where we spoke about train, validate, test. Yeah, I mean, shallow data, this is, going to pronounce your name correctly, I hope, Mohammed Nunul Hoik. You might not have a lot of data. So you may well, I mean, the data I work with, we do not have much data at all. So, you know, I worked with people who be maybe having 100,000 cases to choose from in the last couple of months. They might have 50,000 cases in their model, and they can obviously chop it up a lot. I used to work with data where literally weekly data, 3 years, that's 156 observations. So you're gonna be limited. If you do not have a lot of data, then what you hopefully can do is make a prediction for, in my situation, you're gonna laugh at some of this, but for the next quarter. So make a prediction for another 13 observations. And use that to give you an indication. That's when you're making simple decisions. Clearly, the amount of data you have is going to impact the approach you're able to use. But there's always tricks you can do. You can often chop your data. So you can often take cuts of your data, you know, in my case by geography or, you know, by customer type. You might also be able to resample your data. So you might well find that, yes, you don't have a lot of data, but actually, is there much difference between 150 observations and 120 observations? Can I actually chop it up? So I'm building a model on 120 and then actually using the 30 to give me an indication, and I'm doing that multiple times. So there's always something you can do, but absolutely, the less data you have, the harder this is going to be, and the more you're going to have to think about how you do it. So that was Mohammed. Then Amanda, okay, like the camera analogy, great. How about the significance level? Good questions. Feel free to reach out to me. Happy to have a more detailed conversation about this offline. But, you know, it's going to depend on what you're modeling. So, you know, there's going to be a situation where if you've only got 150 observations, then you can't really put more than 20 variables into your model. Now, in my case, where you're doing a time series, it's, you know, it's really easy to get a high fit, but then you'll still find that some things are going to work better than others, and one is going to be making decisions. So partly it's just recognizing that even if you're not able to do what you'd want to, it's recognizing that if you are making decisions that your algorithm is not, i.e. you're making decisions, your model could be helping you. You could be using a statistical approach to help you make those decisions. So there's always something possible, but the less data you have, the harder it's going to be.
Oh, great. Thank you very much, Tim. Right, and then next up we have Emma. So if you're ready, Emma, I'd like to share your screen.
Yes. And I'm going to share my top and then just try to move things around. And yeah, just minimize this slightly. Can everyone see that? Is that all good? Perfect. Yes, I'm Emma Vestesson. You can find me on Twitter at Gummifort, if you can actually spell. It's a very, very old nickname. And I'm here to tell you about why we used R during COVID-19 in our response to COVID-19, but also monstR, which is this package that we built to kind of help us in our work. And I need to click, I think. So I'm a senior data analyst at the Health Foundation. I'm also a part-time PhD student at UCL, and I'm also one of the R Ladies London organisers, and I'm one of the R Dog Ladies, if people are kind of familiar with this big divide of the R community. And this is just my dog in the corner helping me with a presentation earlier this summer. So for those of you who haven't heard about the Health Foundation, We are an independent charity and we're committed to bringing about better health and healthcare for people in the UK. And we try to do that by connecting what works on the ground with effective policymaking and the other way around. So I'm part of the data analytics team at the Health Foundation, and we have a vision, which is that everyone's health and care should benefit from analytics and data-driven technology. And as part of that, we are also actively trying to support the analytical community in the UK. So I just want to share these two initiatives, illustrated here by two quite bad photos. So there's something called the NHSR community, which is a community for people within the NHS who want to use R more, and AFA, which is a community for health analysts. So if you are someone working with data within the NHS, I'd really recommend checking these two groups out. So I'll kind of start about just telling you what we were doing before COVID. So we had started trying to work a lot more openly at the Health Foundation. So that for us included things like moving over into open source languages. So we were always, some people were always using R at the Health Foundation, but we have more and more people moving over. We started sharing our code on GitHub, but we also started sharing our learning on how we're using GitHub, because we realized that this can actually be quite a tricky thing to do. So when COVID hit, like for a lot of people, that changed our way of working. So first of all, we all ended up working remotely, and I actually ended up working for Sweden for about 5 months. Our workload also increased by quite a lot. We were trying to respond to a lot of data releases. So our work became very active. So quite often there would be a data release in the morning and we would try to comment on it and get something out by the end of the day or the next day. We also quite often wanted to, once we'd done that initial output, we wanted to update it as soon as we got new data, and again, get that out very, very quickly. And as I said, we were aiming to inform policy, so we wanted to be as transparent as possible, because if we said that, X% of people dying of COVID were living in care homes, we want to make sure that people can check that number and trust us. So this kind of led us to being even more committed to being open, but we realized that we needed some kind of pipeline for our open data work that would allow us to analyze data more quickly, but still be transparent and reproducible. So I think compared to the kind of pipelines that Tim talked about in the talk earlier, the one we came up with was actually incredibly basic. So it had 3 steps. We want to download some data, we want to clean that data, and then we want to create some charts and some tables. And we want to do that primarily using R, and to be honest, RStudio, but also by putting everything on GitHub so people can check our work, but also, because we're all spread out, everyone should always be able to access what we're doing on GitHub. So the first step was to get your hands on the data. You can, of course, just go to a website and click download. But I really prefer to let R do all of the work. So we figured out that we can actually do that. So you can download data directly from the internet without leaving our studio, which is truly the dream. And you can do that using base R, or I'm quite a big fan of this curl package. I'm sure there are loads of other packages as well. So all you do is provide one of these functions with a link to where the data is stored. The problem with that is that every time the data is updated, the link changes. It doesn't necessarily change in a consistent way, because it would be fine if it just now said week ending 25th of June, but actually there are often other things changing somewhere else that you just can't predict, which then means you have to go to the website and find the link. So we tried a different approach. We decided that actually we can scrape the link. So we gave it kind of we gave R the main link. We checked that we were actually allowed to go to this website and scrape, and then we read in the website. And by doing that, you can actually end up with all the links on the website, and we could pull out things, and we eventually ended up with this link that we wanted to download the data. The problem with this, even though it works, and I think it's actually quite a good solution, It depends on the structure of the website. So sometimes you go to a website and it just wasn't possible to kind of extract the bit that you wanted, or like the CSS code, or it was really hard and you didn't get, sometimes it was really obvious which bit you wanted, and sometimes it was a lot harder. So you manage to get the data, and you then open the file and you realize that this is what it looks like. So anyone who's tried to extract data from a spreadsheet that looks like this, and this is a very, very common format, because actually it's quite easy to read for a person. I mean, this is very small, so it's not easy for you to read, but if you had it on your screen, it would be. But you know, this is what we had to work with. So we used a few different functions from the janitor package, which is a really, really good package for data cleaning, kind of in addition to your standard kind of DPIR or data table. So I have two favorite functions that I just want to mention. One is the clean names function that will turn your variable names into either snake case or camel case. I'm a snake case kind of girl, so that's what I would go for. But it gives you nice and clean variable names, which is kind of makes your data a lot easier to work with. There's also this remove empty function that will remove empty rows and columns from your data set. So it's quite a quick, nice way of cleaning up your data set. So I was happy with that. But there were other things that I was slightly less happy with. And that was, for example, when we were reading in the data, we would sometimes just drop the first couple of rows, or we would filter on certain rows. But that's actually quite a risky thing to do, because what happens if the data changes next week and you're in a rush and you don't realise? So that left me slightly uncomfortable. So what we did to kind of remedy that situation was that we started writing unit tests using the testnet package to kind of warn us if the data changed. And I think that's actually quite a sensible approach, and that's probably something you should be doing for projects that you're running, kind of even if it's not a package. I think unit tests can be really, really good for analysis, but it's quite time-consuming thing, so we're thinking maybe there's a better way. So we decided to kind of clean up our pipeline, and we ended up working with Neil Swinnerton from a company called monstR. And one of the first things he said to us was, do you know that there's an ONS API? And we didn't, because we had kind of taken this really quick approach, like we need to get this data, we'll download it. So this led to the birth of what we call monstR, and monstR stands for making an ONS table readable. And I cannot take credit for this name, so this was my colleague Richard Bryan who came up with this name, and then Fiona came up with this cute little logo. But what it does is it queries the ONS API for you, and it downloads the data directly. So I realised that a lot of people talk about APIs, including me, and before working on this package, my understanding was kind of like, I don't really know what an API is, but I know that if there is one, then I should be using it. So I looked it up on Wikipedia, and I don't think this leaves me understanding more. But after working on this, I think this is my current understanding. So I think it's essentially a bunch of JSON files that will eventually give me that link that I've been trying to get all along, like I was talking about earlier in terms of scraping and everything. So I'm just going to show you what the API actually looks like when you click on it. I don't think my definition is one that you'll ever find in a dictionary or any kind of textbook. But this is what it looks like when you kind of come to the API, and you can click on, say, this one that says latest version, and you go here and you can scroll down, you can see it says downloads, and it then actually has this file that I can click on, and it's now asked me to download a file. I'm not going to download it. So actually, I think what monstR will do is make it a lot easier for you to navigate those files. So there are only really 3 functions that you need to worry about, and I'll talk you through each one of them. So there's available data sets, available editions, and available versions. And that is because each data set comes with, you have your data set, and that data set has got different editions, and each edition has then got different versions. So the first function that we should look at is this ONS available data sets, and what it does is it returns a data frame. It doesn't actually print very well in here, but it's got an ID, a title, a description. It's got a few other things like when it will next be released and how frequently it is released. So once you've picked a data set that you're interested in, you need to remember the ID. And I've picked this weekly deaths region because that's the data set I was showing you earlier that I was trying to clean. So once I have an ID, I feed it back into this available editions function, and it will return the different editions that you can use. And then there's also a function called available versions, and again you feed it the ID and the edition, and it gives you the different versions. This step is kind of optional. Later on when we're downloading the data, you'll see that if you don't specify the version, it will default to the latest version. And to be honest, that's probably what you want most of the time, but should you want older data, you can also do this. So this is a full pipeline, and I'm essentially in my head split into 3 different ways. So when I said earlier, you only need to worry about 3 functions. Those are the ones that you really need to interact with. I think once you've done that, you can kind of just copy this full pipeline setup. So there are the first 3 functions, and I realised that here I should have specified the edition as well. It will go, I think, for the first edition or the most recent edition if you don't specify, but I'll check that. So these first 3 functions essentially set up your pipeline, so you can tell it where it, so if you don't say anything, it will download the data to a folder called data, original data, raw data, and then the edition and the data set name and the edition and the version. And these functions just kind of set that up for you. The ONS download function does exactly what it says on the box. So this is the one where it will download the data for you. And I don't know if you remember earlier when we were looking here, for example, there are different formats of the data set, so you can specify which one you want. And then these last 3 functions are kind of optional. So once you've run everything down to ONS download, you will have the data. These last 3 functions essentially take those files that you've downloaded, done a tiny bit of cleaning, which to be honest at the moment is just running the clean names function, and then it saves it as a CSV, XLS file and an RDS file for you in a clean folder. So it's really, really ready for use. So I had a few things that we actually learned building our first package, because this was the first package we built at the Health Foundation and kind of released out in the open. And the first thing is just a plug for the use this package, because it makes package building so easy. Like all you have to do is kind of put in use and then whatever you want to do, and it will just sort everything out for you. It's really great. But also the package down package, which makes it really, really easy to set up a website for your package, which I think just makes it look a lot more professional very quickly. But also GitHub Actions, because it lets you automate the boring bits. And you also get these cute little badges for your README saying that your package is building properly or how many contributors you've got. And I think GitHub Actions for us was one of those things that it seemed really complicated before we got started, but actually was really easy to set up. And there are actually, again, functions that use this package for you to use. So we're not done with this project. So this is something that's still ongoing. So we know that we want to improve the documentation. At the moment, there's just one vignette. So we're working on a few more. We want to add some more unit tests to make sure that the code doesn't fail. We're hoping to work with someone from the ONS maybe to see, even if it's just to find out where the package is going next. And we've interacted with them a bit and they've been really helpful. And we want to start using this for live projects, because so far this is something that we've built but we haven't been able to use yet because of the timing. But the next step is actually to build this into our pipeline. And I also would be really, really happy if you wanted to try monstR. So there are instructions on how to download the package. Just file an issue if you like it. If you don't like it, suggest new features. Tell us that you like the logo. Tell us that you don't tell us that you hate the logo. Essentially, just interact with it and tell us what works and what doesn't work. And yeah, that's it from me. So I want to say a big thank you for everyone who's listening, but also obviously everyone who's contributed to the package. And you can find a list of all the contributors on our GitHub page. But a special thank you to Neil, who wrote most of the code, and Fiona, who designed a little monster logo, and Richard Bryan, who came up with the name. So thank you.
Great, thank you very much, Emma. Cool, if anyone has any questions, feel free to type those into the chat now. Just give people a minute. Also, we've got, can you see the chat questions, Emma?
Sorry, I'm trying to figure that out.
If not,
my
I can read
Zoom
it
has been,
to you.
yeah, my Zoom hasn't been great today, to be honest. It keeps going to the...
So, okay, here we go. One question. What's the hardest challenge when building a package?
I think it's kind of deciding what's in scope and what's not in scope. So both in terms of, I think it's very easy to put too many things into a specific function. So you might want it to do everything, but it's probably a better approach to have, many functions doing, one thing well. But I think it's also quite tempting to just put a bunch of functions into a package rather than splitting it up too many. So, but I think you can go kind of both ways. So I think getting that kind of thing right, because you don't want your users to have to run 10 functions to do something very basic, but one big function will eventually fail because it's really, really hard to maintain.
Great, thank you. I've got another question from Caroline, who says that she loves the logo and the name. Do you know if every ONS data table available via the API?
So it's not, no, so you can't get all of the data that you can get from the ONS directly from the API. I think there's about 50 different data sets at the moment. I think this is where, and I know there are actually some people from the ONS here, so if they want to, comment on it in the chat, you're more than welcome to. I think they're going to continue to add data sets. This API is still in beta, so there might be changes. But it has all the mortality data sets, which I think is what kind of brought us to in a very morbid way, brought us to the API.
Great, okay, I think that is all the questions. But if anyone does have any more questions for Emma, please feel free to message her in the chat as we go on. And then last but not least, we have Mark. So if you'd like to share your screen.
Thanks, Laura. Okay, so share my screen. Okay, so I hope everybody can see my screen now. So my talk is about using R, Docker, and microservices to create a highly scalable machine learning system. So just an introduction on what we're going to cover today. So first of all, we're just going to cover Docker and why you would use Docker. We're going to show an example of creating a Docker container for an R Shiny application and hosting it on AWS ECS, which is Elastic Container Service. We're going to talk a small bit about microservices then after that, and we're going to look at taking the R Shiny application and separating out the user interface in the machine learning component. And the final part, we're just going to have a brief discussion on the advanced level production systems, about how you would actually make that system scale up for handling a high load, how you would manage it using DevOps, infrastructure as code, and talk a small bit about frameworks for microservices, which is Spring, and just talk about managed platforms. So first of all, who are AltViz? So AltViz is a London-based AI company. We're basically VC-backed. We're operating over 7 years, and basically we work on creating automation systems, which can include machine learning, but a lot of times it will include things like BPM rules and other kind of technologies as well. So our kind of catchphrase is we try and make intelligent automation simple. Who am I? So basically, I have 24 years experience as a software developer, BI developer, and the last about 10 years in data scientist. I've co-authored a book in R and deep learning. Chief data scientist at AltViz. But I suppose my primary interest really is trying to get machine learning systems into production. So I'm solutions architect certified under AWS and also AWS certified developer. So basically, as I say, my key interest is really trying to get machine learning models into production. So why do I think this is important? Well, according to a recent survey, 87% of data science projects never make it into production. A lot of this is because most data scientists do not have skills in how to actually create a scalable production system that can handle, a lot of concurrent queries. They don't have experience in DevOps and continuous integration and continuous deployment systems. They don't have experience in messaging queues and scalability. And they also have issues as well with a lot of times with trying to actually do the data engineering both for the ingestion and for the output. So microservices is an architecture or framework to build loosely coupled, highly scalable systems. And it's my belief that it's the ideal way to actually create production machine learning systems. There are other ways, for example, Spark, but I think microservices is actually a better system to actually create scalable machine learning systems. So I'm going to start with Docker and just discuss kind of what Docker is and looking at why you would use Docker. So if we look at the history of software, maybe 20, 30 years ago, we installed software on physical hardware. The disadvantage of this is that you basically have a single box and you have to right size the box or put in the hardware requirements to handle the maximum load. That means that that actual box is underutilized 90% of the time. So we started using virtual machines, especially in the cloud, to kind of divide up the actual processing power of a lot of PCs. The problem with virtual machines is they have a full OS for every virtual machine, which basically means that each virtual machine is very resource intensive. Docker containers are more lightweight. They run as processes rather than as VMs. That means they're better performance, but more importantly, critically, they're faster startup times and greater compatibility across the deployment environments. And they're a key part of microservice architecture because they allow for things like infrastructure as code and portability. And you can always start with Docker images by looking at repositories that already have official images. So the main one is hub.docker.com, which we'll see in a second. So we're going to go through a demo and we're going to try and basically take an RShiny application. We're going to try and create this RShiny application and put it into AWS in a couple of minutes. So hopefully this will work okay. So we're going to start off with looking at Docker Hub and we're going to see what actually images are available in Docker Hub for RShiny applications. So as I mentioned earlier, Docker Hub is basically a place where people have created pre-existing or pre-canned installations of software. So for example, this is a popular profile for R, and there's various container images here that you can use to create to start as a base for your platform development. So if we scroll down here, we'll see that we have a base Ubuntu image, which is Unix OS. We have a version with tidyverse pre-installed in it. We have a version with RStudio pre-installed with it. And this is the one we're actually going to use. This is actually a version of the Docker file that has RShiny and tidyverse packages installed in it. And this is a great starting point because this basically means that when you actually use this container as a base container, you basically don't have to worry about installing those packages. They're already taken care of in your application. So what we're going to go through, if I just go back to my presentation, okay, we're going to look at the next step is we're going to look at the directories in the Docker file and how you'd actually create a Docker file from it. Now to do this, I'm going to use a cloud environment called AWS Cloud9. AWS Cloud9 is just very quickly is a part of AWS. What it is it's a cloud integrated development environment. The advantage you get with Cloud9 is it automatically integrates with the security components within AWS. So you basically are already logged in within the system. So it gives you kind of a machine that you can basically use, that you can run commands on, but it also gives you a browser as well that you can upload files and things like that as well. So what I've done here is I've uploaded 2 RShiny images. This is my app in my RShiny application. You'll see server.r and UI.r. So I can open any of these files and I can edit them within the actual application as well. So I have, for example, my UI and my server, and I can basically make changes as they are. Now, let's go look at the actual Docker file that is actually used to create this application. So as I said, we start off with this version of Rocker, and we basically say we're going to use this basic package. Docker files are basically then have a series of commands that build up the actual Docker file in components. So what we're doing here is we're just running a series of Unix commands to actually install additional software. So sudo apt-get update just basically ensures that the container has all the existing packages, and then we're actually installing a couple of additional R packages inside the application here. So as you can see, you have full control that if you want to install any kind of additional libraries like Random Forest, Shiny Dashboard, Forecast, you can actually install them inside your application. We're then going to copy this folder called Shiny app into the Shiny server folder. We're going to export port 80, which is just HTTP, and we're going to change the config file as well. Okay. So the Shiny app folder is a folder that is in here. It has all the files that are needed to create the R Shiny application. As I said before, the server.r and UI.r. It also has any data that is inside it. So it's a self-contained folder that has all the data and the R scripts that you need to create your R Shiny application. I'm also copying in the config file. The reason I'm copying in the config file is because just to change the port, by default, R Shiny listens to port 3838. So I'm just changing to port 80. And that's matching as well what I'm saying here on the Docker file to expose port 80. And once I have this kind of recipe or Docker file, I can actually build the actual application or build the Docker file. Now to do that, I'm just going to go back to wrong application. To my file here, and I'm just going to build the application within the actual Cloud9 environment. So first of all, I can look at what Docker images are already on Cloud9. So I've actually done a couple of examples here in R Shiny 1. I have the base image Rocker Shinyverse also installed, but I'm just going to build a second version of this application here as well. So what I'm going to do is I'm just going to build a Docker file. What you do is you start in the folder that you want where the Docker file is in. So in this case, it's R Shiny 1. Okay, we'll see my Docker file is within that folder. And just to create the file, I'm just going to go Docker build -t R Shiny 2. So I'm giving it the name R Shiny 2 just to differentiate it between the file is already there. Once you do that, it goes through the Docker file and it basically runs what you call the script and downloads what you call the thing. So you can see here, it's actually downloading the R scripts here and creating that Docker file. Now the advantage is once this is finished, my Docker file is complete and I can install it and all those packages are pre-installed in it. It's also a great way as well to ensure that if you want to ensure that your packages are in a certain version and that they can't be updated, you can do it this way as well because you can actually download package versions as well inside it. So this will take a couple of minutes to run. I just probably just going to stop it because it'll take maybe about 5 or 10 minutes to run. But you can see here, it's actually in the step where it's actually downloading the R packages. So I'm just going to interrupt it there for a second. The next step will be to actually take that Docker file and to upload it into the registry. So to do this, you basically just create a repository in AWS. I'm just going to call this application, and I'm just going to say AWS create repository R Shiny 2. And once I do that, it's going to create a place for that repository if I wanted to upload it. Now, since the actual package didn't upload, I'm not going to actually go to the step of actually uploading it. But the next step, if I wanted to push it up to that repository, would be to tag it and basically then just say Docker push, which will push it up that repository. So when I say repository, we looked beforehand at Docker Hub. Docker Hub is a public repository, but the repository I'm pushing it up here is into AWS, which is the Elastic Container Registry, which is a private registry you can have for your own applications. So here I created a kind of a blank. This is the R Shiny 2 that I updated. There isn't actually any packages here, but we actually see that there are a couple of existing packages here as well for the R time demo and the R TV SVM, which is a prediction model. So once I've created those repositories or those Docker files and I've put them in the repository in AWS, the next step is to actually get them running. So basically what you do is you go into AWS ECS. I have a cluster already running here. The next step is to actually create a service within that application to host that actual container image. So to do that, you go into the container, you say that you want a new service. Once you do that, you have two options, Fargate and EC2. Just very briefly, Fargate is a kind of a serverless offering, whereas EC2 will actually create physical servers that you can actually manage and you can host. Whereas Fargate, basically, the hosting and the management of the actual servers behind are done by AWS behind the scene. So once you do that, you can actually update what's called a task definition. So here my task definition for my time demo. This basically is linked to the container image. You can call it a service name. Give it whatever name you want. You can say you want tasks. So for example, you can create as many tasks as you want. So it'll create how many running instances of that container you want. You can actually put in health checks to make sure that it's that if any of the instances stop responding, that they basically are taken out and they basically are replaced. And you can also control things like deployment type and things like that. So I'm not going to go through the step of configuring the actual server here because I actually have one running already. So if I go into the TS service, and if I look at tasks, I'm just looking for the public IP that this actual server is running on. And if I go to this public IP, we'll see that the actual service or the actual R-Shiny application will actually come up. Will actually come up. So on this application, what we have is it's a very simple application which is to do with time series prediction of items. There are a number of items that we're trying to do a prediction for. And basically what it does is it's showing an item, it's showing the actual values, and it is, sorry, go to the screen instead. It's showing the actual values, which are in blue in this graph, and it's showing predicted values. Okay, and what we have is we have a series of algorithms that are here within the application. There's a linear model, there's a moving average model, and there's a previous value. Probably the best one to look at is the previous value because you'll see it's just time shifted. And basically for each one of these models, it's just showing the actual predicted and the error rate and the overall error rate within that actual application or within that for that model. So what we've seen here, you've seen Docker Hub, which is the base, which has a series of base containers you can use to create your own applications. So we use one that has tidyverse and R-Shiny installed. We've seen the directories and directory structure of the Docker file and the config file that you need to create an R-Shiny container. We've seen the Cloud9 environment, which basically is just a cloud IDE within AWS, which basically has Docker already installed, so you can quickly integrate with the services and the command line interface of AWS. We built the Docker container, we pushed it up the repository, we created a task definition, and we created an ECS service, and we saw the R-Shiny container running on the server. Now, that seems like an awful lot of work for not much gain, because you could ask the question, why can I not just put the R-Shiny application on an EC2 server? And yes, that would be easier if that's all you were actually looking to do. So the next step we're going to do is look at microservices and splitting the application into two parts, the UI part and the machine learning part. So why microservices? Again, if we look back at the history of software, in the beginning, we built software as a single unit called a monolith. The application that I show in the R-Shiny application, for example, is a monolith. It's a single application. There's no different installation parts. You install a single application for it. The problem with monoliths is that they have long development cycles, and they don't take advantage of the expertise of different teams. So all the people in the team, whether they're working UI, business logic, or database teams, all their work has to be integrated. And as the application size and the complexity increases, this makes it more difficult to deploy. So you get down to the state where basically nothing is deployed for 6 months or 12 months. and then you have a big kind of push to get everything integrated into once, which is which just a lot of times ends in disaster. So microservices is an architecture or framework to address the problem of monoliths. It's becoming very popular in software development for enterprise and large-scale systems now. So the idea is, instead of having one large application, you have a lot of smaller applications. And each team can take responsibility for their own application or their own microservice. And they can make whatever changes they want to the microservice, as long as they ensure that the interface or the signature between the microservices stays consistent. So if they want to refactor or rewrite part of the application, if they want to strip out one database and put it in another database, they can do that as long as they maintain that the signature that people that calling that application or that microservice stays the same. They can do whatever they want to the internal workings of it. Microservices use HTTP and JSON used for communication. But a microservice can be written in any language that basically supports these. So you can write microservices in Java and Python and R. And we'll see one, for example, in R in a minute. And a key part of microservices as well is it can scale up or down independently. So what this means is that if you can scale up microservices independently, you might have only a few components, for example, for the UI. But if you have a heavy-duty machine learning GPU prediction service at the backend, you can scale that up to have multiple microservices at the backend. So the microservices can be built by different teams. The UI team can build their UI in JavaScript. The data engineers can build their data ingestion microservice in whatever application that programming language that they prefer, usually Java. Data scientists can build the machine learning microservice in either R or Python. So each team can work on the tools that they want without being forced to basically pick the lowest common denominator. Microservices then use load balancing or message buses from fault tolerance and for scalability. And as I said before, one of the major benefits of having microservices is that each component can be customized for a particular runtime. So for example, in the machine learning prediction service, you can have an infinite number of small services to basically do the prediction. Or you might have a customized heavy server that is CPU optimized, basically that because you know that it's going to be mainly run on a batch system. You can use specialized hardware, for example, GPUs. And that means that just the machine learning microservices on a GPU, not the entire application wasted on GPUs on a GPU server, when it's only a very small part of it that actually needs GPUs. And each one of these microservices, and particularly the machine learning microservices, can scale up and down according to demand. You can use spot instances of cost optimization and so on. So just looking for, I'm going to go back to the demo for a second. And what I'm going to show is back to the Cloud9 environment. And I'm just going to basically show that in the Cloud9 environment, I have a second R-Shiny application. This is using RPlumber. I'm not going to go into details what RPlumber is, but basically what it allows you to do is create a REST API endpoint for your machine learning service. So what it is it basically takes a series of input parameters across that is sent through REST API, and basically it responds back with a prediction algorithm. So this is a very, very simple API. What I have done here is offline, I have written four different machine learning models, and I saved them as RDS files, which is the data files. So basically the model is stored within these files. I'm passing in a parameter. The parameter is M to say which model I want to run. The reason I'm passing in if I go back to the application, within the application, I have four different items. So I have a different model for each one of these items. So I'm not using a global model. I'm using a model particular for every single one of these items. And I'm basically saying that depending on the parameter M, I'm basically taking the values I'm taking the values from another object df, and I'm basically predicting it for that. Now, I actually have an example within the actual application for this. So back to the application. And inside in here, I have a diagnostic screen, which basically shows what's actually what's actually sent into the model. So what I'm doing is I'm sending into the model a series of parameter values. And basically what I'm trying to do with this time series algorithm is showing the values for the last 6 weeks, showing the values for 52 weeks ago, approximately 52 weeks ago, and showing the value for 104 weeks. So I'm basically trying to see what happened this week, what happened this week in the last year, what happened in this week 2 years ago. And the reason for that is just to capture any seasonality within the actual system. There are other ways to do it as well. But what I can do then is I can test this API. Hopefully it'll come back with a value. Okay, we will try and see what that is now. I think I know what that is. If I go to my cluster, if I go to my service, I have my prediction service here. I just want to check something on prediction service. I believe that maybe I don't have the API. That's right. I don't have the IP address for a service. I'm just going to go back to, sorry, okay. So what I need to do is just put in the IP of the service within here, test API again, and it's actually after coming back with a response. And I can actually see this response here as well. So basically this is a diagnostic screen. I actually have inside the application here as well. I have my Docker model SVM written inside here as well. So now that I've set my public IP address, it basically goes along and basically calls the prediction algorithm from a different Docker container. Okay, so what we've covered here, again, we've looked at our plumber, we've looked at the directories in the Docker file. I haven't built a Docker container here or done these other tasks because we've already seen these. But basically, I've separated out the UI and the machine learning prediction. Now that I've separated out the machine learning prediction from the UI, the application is a lot more modular. If another team wants to come along and basically build a web UI over the actual application rather than using our Shiny, the prediction algorithm is there. If the prediction algorithm suddenly scales up, we're getting hundreds of thousands of users, I can basically put the application, I can scale up just the actual machine learning prediction part without having to deploy the complete application within it. It also means I can do things like call it from batch mode, I can call it from other services. I can even make the API available publicly, and people can actually call the API from other services if I make that, if I decide to allow it. So moving forward, what would we do to improve this application? Well, first of all, that I would look at is basically look at applying looking at scalability on the machine learning service. So basically, there's two options for that. You can use a load balancer, and this basically means that I can create what's called an auto-scaling policy to scale up and down the number of workers and number of servers that does the machine learning prediction according to demand. And this actually happens automatically. So what you would do in AWS is you basically would set up a series of rules to say, for example, if my CPU utilization across my machine learning prediction workers started going up by 80% for 5 minutes, then add more workers to the actual application. And similarly, if the CPU utilization dropped below 20%, then remove some of those workers from the actual pool. So load balancing and auto-scaling can be done at multiple levels. They can be done at EC2 level, ECS level. You can actually use Kubernetes, which is what we use internally as well for it. Load balancing and auto-scaling is okay for web endpoints. The disadvantage of load balancing is that it can be actually slow to respond to volatile traffic patterns. What this basically means is, again, going back to the example I said about that it takes 5 minutes, that you basically, the rule is that you wait for your CPU utilization to go over 80% over 5 minutes. If you suddenly get a very, very heavy spike of traffic over 1 minute, it's not very quick. It doesn't add machines that quickly. And typically there's a cool down period as well, which means that if it adds a machine, it waits 5 to 10 more minutes before it decides to add more machines. And an alternative architecture is to use message buses, which is actually favored by microservices. And this basically decouples the applications from calling each other. So this is an example architecture we built for a speech recognition system that uses deep speech or AWS transcribe to actually do transcription. And basically, we have all the actual components as separate microservices. And this message queue acts as a kind of a buffer, so no one microservice can get swamped or basically can start holding up the entire system. If, for example, there's a lot of files come in the audio adapter and the deep speech algorithm or the deep speech microservice can't actually process them all at once, that's fine. They'll be stored in the message queue. And as they're processed, they'll be the deep speech microservice will pull messages from the queue, process them, and put them back into the queue again. Basically means all your microservices run asynchronously and they're not directly connected, but it means that your system is a lot more scalable and a lot more fault tolerant. It also means as well, just to comment that in here as well, you can call external services, for example, AWS Transcribe inside here, which is an asynchronous service as well. So you just basically put in a request to AWS Transcribe to transcribe some audio, and basically it will respond back in time. It doesn't come back instantaneously, but your application isn't in a holding pattern waiting for a response. It can actually just run and continue processing, and the other microservice can continue processing independently of it. So I just want to kind of close out on a couple of key points about our kind of like microservices as well, DevOps, infrastructure as code, and frameworks, and just a brief introduction to Spring. Another problem with monoliths, and I touched on this earlier, was that different teams were responsible for developing and supporting the system. So what might happen in a monolith is you have a development team who are responsible for developing the application, and then you have what's called an operations team, which is responsible for supporting the application in runtime. And again, this causes massive problems with large-scale applications in that the different groups have very, very different ideas. So the operation team don't want change, the development team do want change, and it causes conflict within those teams. So DevOps is, the core idea in DevOps, I suppose, is that the people who build the code are responsible for supporting it. Infrastructure as code is a key part of DevOps. It means that you basically don't try and manage servers. You basically try and write all your code to manage servers, including configuration as scripts. So you might use something like AWS CloudFormation, which creates your services and creates your applications. And the idea here is that you can quickly move your application into a completely different environment because everything is stored within code. So the idea is you don't have anybody logging into servers and trying to install software. That should all be automated within code. I suppose the problem with DevOps and infrastructure as code and all this is that it gets very complicated very quickly. Most machine learning platforms focus on model building and not model deployment. We built an application to deploy machine learning models at scale. What we have found is that of all the application systems that are out there that support that are so-called ML platforms, very few of them manage the deployment of applications and machine learning at all. Some of them will offer you the ability to create the REST endpoint, but very, very few of them allow you to create a REST endpoint that actually has the scalability and the fault tolerance that is required in an enterprise application. Sorry, go back one way. So as an example or an architecture of, I suppose, what we would say is a machine learning platform. This is an architecture we've done for, for a sample architecture, where you basically have the key microservices, which is for example, for authorization, for discovery, for config, for load balancing, for single sign-on, for an API gateway, for load balancing, for circuit breaker, which is fault tolerance. You have all those applications or microservices embedded within the application, and then you embed whatever service you need for machine learning, voice transcription, or NLP within the actual application. And all these purpose services can be written in R or Python, and basically the other applications or the other microservices work around those applications and know how to call these applications. And this is because, again, looking at kind of what you would have, I won't go through this slide in detail, but basically it just shows kind of like what you actually expect in a kind of a full-blown microservice architecture. So first of all, you expect it to be cloud native, which basically means that it can run in the cloud, but can also be deployed in-house if need be. So cloud native basically means, also means as well that it can be installed in any environment, so AWS, Azure, or Google. You have microservices and what are called micro front ends, which basically allows for the front end integrated in JavaScript, Java for core services, or in Python for machine learning. You have things like container and container orchestration, which I didn't go into detail, but basically Kubernetes is the way to actually manage Docker containers in a running environment. You're also looking at what's called DevSecOps, which basically adds security to DevOps, basically to ensure things like single sign-on, but also to ensure that the containers that you create are scanned for any vulnerabilities. So we basically ensure that any of the containers we use don't have packages that are out of date, and basically also include penetration tests and so on like that. And finally, just on the DevOps side, you have DevOps monitoring. So basically using things like Humio, AWS CloudWatch, Prometheus, and Grafana to basically ensure that the application is running as it's meant to and to actually store the application. So just to finish, microservices are an excellent way to deploy machine learning systems. To start with, if you were going on this journey, what I would just say is just start with separating out the UI and machine learning into different services. I could literally have spent, I suppose, 2 hours actually demonstrating in detail how this would actually be done. But I think the key part of this, actually, if you're to take anything out of this presentation, it's not the how you would do it, it's why you would do it. And you do it because basically it makes your application more scalable and more responsive. If you wanted to start off separating the UI and machine learning into different services, you don't really need Docker. You can just start with EC2 VMs at the start and just actually have one running UI in R Shiny and have R Plumber and doing your machine learning prediction. But Docker allows you to create a deployable application or microservice, which can be, deployed on AWS ECS, it can be deployed on Azure, it can be deployed on Google, and just basically means that you can, integrate with those actual environments. And it also means that you can start doing the next step, which is consider how your application will scale. So as I said beforehand, of the applications that we've seen in machine learning platforms, while some of them do allow you to create a REST API, the problem we have with those platforms is that they don't allow you to auto-scale, or they don't handle the fault tolerance within that. Which basically means that if you want to create a REST API to do prediction, you have to create you have to host it on a server that basically is probably over capacity 90% of the time. Whereas with Docker containers and all the scalability, your application can scale up and scale down according to demand, which makes it a lot more cost efficient. So consider your complexity. If it's a very simple application and you just want to start experimenting to this, then basically, as I say, separating the UI and machine learning into different services will get you 90% of the way. For more complicated systems, then you just decide what machine learning platforms actually support what I want to do, what ones actually allow me to create separate services for the UI, separate services for the machine learning, and how do they actually scale and respond to the demand over time. So that is it. I'd like to thank everybody for following along, and if there's any questions, fire ahead.
Great, thank you very much, Mark. There's a couple of questions in the chat. Would you like me to read them to you?
Sure, yeah, thanks.
Amanda has said, for Docker Hub, you said that packages already installed. If you want a different version, for example, more recent or an older version, can you update a package?
Sure. So if I go back to the Docker Hub, so these things, all Docker containers or images kind of work as kind of layers. So if you wanted a previous version, if I go to the Rock or Shinyverse, the actual recipe or the Docker file is actually contained within here. So you'll see what this person is doing to create this Docker image. He's starting off with another base one with Shiny. And basically then he's running a couple of Unix commands to install additional software. And that basically, he's also installing as well some additional R tools. So you can start with any of these applications And if, for example, you're not happy with the tidyverse version that he's running, you can start with just the base image that he has, rock or shiny, and then install whatever version of tidyverse you're doing you want down here. So if you see what's happening here, he's starting with rock or shiny. He's calling a series of Unix commands to install some libraries that are probably needed by the R-Shiny applications like XML, SSL, and things like that. But you see down here, he's installing the dplyr and tidyverse. And that's where you could basically take this Docker container, modify it as per your own requirements, and install whatever version of the package you actually needed within the application.
Great. And then we had a question from Amit. Is it possible to deploy a Shiny app directly using something like AWS Lambda? Is that right?
AWS Lambda does not support, or it does support Python. So AWS Lambda is a serverless architecture similar to, I suppose, kind of ECS, but usually you can install a Lambda server to do the machine learning, but only in Python. It does not support R at the moment.
Cool. Right. I think that's all the questions. Great. Thank you so much to our speakers, Tim, Emma, and Mark, for some great presentations. And thank you for everyone for joining us. I haven't got anything planned for September yet. We're kind of putting all our energy into the Earl plan. So if I do plan something in September, I'll let everyone know as soon as possible. But yeah, check out the Earl Conf website for information on the presentations and the workshops there. And it's great to see everybody, and have a great evening, everyone. Bye.